Hey guys, welcome back to Engineering Hack, where we try to solve engineering problems in a way that's hopefully easy to understand. Today we're looking at the final exam on Thermodynamics 2021. The exam has 4 questions. It's actually 3 and the third one split into 2, so 4 in total. We're going to make one video for each. The first question, the one we're about to tackle, is a bit longer, so we might need to break this one too. The problem reads, the air standard, and we can go ahead and do this. The air standard Atkinson cycle consists of the following 4 closed system thermodynamic processes. So an adiabatic and reversible compression, a constant volume heat addition, adiabatic and reversible expansion, and a constant pressure heat rejection. So we can go ahead and do this Atkinson cycle. Let's go ahead and do, let me just, do a little thing here. So we first have a adiabatic and reversible compression, okay? So because it's adiabatic and reversible, we know it's going to be something like this. It's going to take this shape, okay? So it can go either that way if it's an expansion or this way if it's a compression. So in our case, it's compression. So it's going to be something like this, okay? Then the next one is a constant volume heat addition. So if this is volume, right? So it has to stay on the same line, so it has to go upwards. Why upwards? Because we're adding heat to it, so we expect the pressure to increase since the volume cannot. Then we have a adiabatic and reversible expansion. So same thing as the first one, but now we're going on the expansion way, so we're going that way. Then we have a constant pressure heat rejection. So again, constant pressure. So instead of staying on this axis here, it has to stay constant on this axis here, right? So that means that we're going to have a line like so. And which way do we expect it to go? So we're doing blue. Which way do we expect it to go? We expect it to go this way here because it's rejecting heat, right? So if it's rejecting heat, it's losing energy, and we expect it to decrease its volume because of that. In a real spark ignition reciprocating piston engine, the Atkinson cycle can be realized by means of a special linkage or by clever control of the valves. This type of engine would be useful in a hybrid powertrain. So it's actually used in some hybrid motors, hybrid engines, and I'll tell you what it uses it. At state 1, the pressure is P1, 101.325 kilopascals, and the temperature is 20 Celsius. The volumetric compression ratio is 9.5, and the ratio of the volumetric expansion and the volumetric compression ratio is 2.25. So then what do we need to do? Draw the cycle in the PV diagram, write down the answers for all the states according to the table here. So they want pressure, temperature, and specific volume in all the states. Find the heat, so it wants the heat for each of the 4 parts of the cycle, as well as the work for each of the parts of the cycle, all in kilojoules per kilogram. So know already that we have an indication that we're not going to be finding mass throughout this problem. We also want to calculate the work net, so we know this is just right on the side here. That's going to be the difference between how much heat was given to the system, how much left, or we can also do this as, no, just leave it like that for now. We can also sum up all the works, right? That's another way to do it. We can sum up all the individual works throughout the cycle. And then calculate the thermal efficiency of the cycle. Again, we know how to do this. Thermal efficiency is just how much work, thermal efficiency, just how much work we actually got in respect to how much energy was available from the start, which because of this idea here can also be written as the difference between Q in and Q out divided by how much energy was there to begin with. Okay, cool. We're taking CP as a constant value for air. So this is great because it simplifies a lot our relationships, and also taking the R already with the kilograms in it. Okay, so that means that whenever we're doing PV equals nRT, PV equals nRT, we're actually doing M, not N, M for mass, because we have a R that's given in kilograms. Brilliant. What else do we know? We know that K is 1.4 for air, and because we're considering CPs and CVs to be constant, we know K is just a ratio between CP over CV. So that means that we can find CV if we want to. So that means that CV would just be 1.005 divided by 1.4, and that gives me, what does it give me? It gives me about 0.718. Great. Could have memorized that too. Okay, so we have all that information to help us out as we go. Brilliant. Let's start. First thing we need to do is draw the PV. Well, kind of did already, right? Just need to combine all these figures here. So let's do it here to the side. We're going to do the PV diagram for this fellow. P and V. And the way I'm going to do this is, specific one, the way I'm going to do this is actually going to start with the 2 ones that are constant something. Okay, so I'm going to start with the constant volume. And this is from 2 to 3, if you recall, 2 to 3, right? The constant volume process, here, this one here. Constant volume heat addition. And the other one, which is the constant pressure heat rejection. So that's the We'll do down here. Here, cool. So this is 4 and then back to 1. And now what I'm going to do is I'm going to tie these guys up. Let's change color so that there's actually, you can see the difference. So this is 1 adiabatic. Remember adiabatic has to be set like this. So I'm just, tying them up. And then obviously we're going in this direction in which the numbers increase. This is our cycle. So from here to here, this is adiabatic compression. Okay, adiabatic and reversible, no change in entropy. From here to here, we have a heat addition at constant volume. From here to here, and probably want to make this more, like so, more like a curve instead of a straight line. So from here to here, we have, again, adiabatic and reversible expansion instead of the compression. Again, entropy does not change. And from here to here, we have the heat rejection at constant pressure. Okay, so let's remind ourselves that here we have a heat addition. So this is our Q in. And over here, we have our Q out, heat rejection. Brilliant. What else can we tell from this drawing? We can tell that the work, okay, so the work is going to happen as we go from 3 to 4, and this is going to be the work, right? The area under the curve. It's going to be the work from 3 to 4. And from 4 to 1, we have this work here. And then from 1 to 2, we have this work here. Okay, so this is kind of the work on the compression side of it. So we need to give that energy for the system for it to be able to compress it. And then from 3 to 4, the yellow one that we drew before, this is the one it's releasing as it's expanding. And then obviously because we want the net work out of this, what we're looking for, net work is going to be the difference between the two areas, which is the area inside the cycle, right? So this area here that I just drew, that will be our net work. Cool. All right, so part A is done. Part B. In your answer, create a table like that below and fill the missing information for state 1, 2, 3, and 4. Okay, so pretty much solve the whole thing. That's what they're asking of us. We can start with the first one. The first one is very straightforward. This is T1, okay, in Kelvin. All right, so let's do this. So part B. So T1 is 20 Celsius. So this straight off the bat, 293 Kelvin. So that's done. And then we have the pressure it's given, so we can find a specific volume, right? So because this is an ideal gas, let's do this here because ideal gas, so we can approximate air to an ideal gas. That's 100% fine. So then we can use PV equals nRT, mRT, and therefore if we want to find V over M, that's just going to be specific volume for state 1. That's simply going to be RT divided by P, all of which we have, right? 2.87 T293, and P equals 101.325. Brilliant. Unit-wise, what do we have? We have kilojoules per kilograms Kelvin on the R, we have Kelvin on the temperature, and we have kilopascals on the pressure. So what happens here? Well, Kelvin and Kelvin go away, and then our kilojoules, our kilo and kilo go away, and then our joules and pascals is going to be meters cubed. So that's going to be meters cubed per kilogram, which is perfect. Exactly what we're looking for. This gives me 0.8299, so let's go ahead and approximate that to 0.83 meters cubed per kilogram. Cool. So that's our first state. This is state 1. Let's actually write that down. Let's write that down. State 1. So state 1 is done. So we can go ahead and do state 2 now. State 2. So we don't have any information for state 2, right? We don't have temperature, we don't have specific volume, we don't have pressure. So we can't really use PV and RT to save us. What we need to do is find at least 2 of these guys here, these 2, or any other 2 that want these 2, so that we can then use PV equals nRT. What we do have is a relationship for the ratio between the volumes. Here it is, between state 1 and 2, which is 9.5. So that's very straightforward, right? So specific volume on state 1 divided by specific volume T2 equals 9.5. So therefore, we can easily find the state volume 2 just going to be like a tenth, almost a tenth of the 1. So that's just 0.087 meters cubed per kilogram. So that's straightforward. The other thing we can use to our advantage is that we know that from 1 to 2 we have a adiabatic adiabatic plus reversible compression. And we know that in this case we have ideal gas considering constant CPs and CVs, and we have an isentropic transformation, right? So we know that there's a relationship that because of that, which says that P1 V1 to the K equals P2 V2 to the K. We don't have the actual V's, but we have the relationship between the two, right? So we can do, okay, so that means that my P2 will just be my V2 over my V1, to the k times my P1. And we have all this because we know that that's just 1 over 9.5. And oops, actually 9.5, right? Yeah, sorry, 9.5. And this is 1.4 k, and P is just 101.325 kilopascals. So that means that P2 equals 2,368.8 kilopascals. Great. So these are the things we're looking for, right? This guy, and then like I said before, we have two of the things. So then temperature is trivial because we know we can just use the ideal gas law. So temperature will just be PV divided by MR. We have specific volume, which is this, and we have everything else. So 2,368.8 times 0.087 divided by the 0.287, which gives us about 721.1. Cool. So state 2 is done. Okay, state 3. State 3. Once again, we don't know much about state 3. We don't know anything about state 3. What we do know is the relationship between states. Let's go back to our, there you go. We have this guy completely figured out. We have this guy completely figured out. Now, we don't know anything about this guy. And actually we do, right? We know that specific volume is the same. So we know the specific volume, but I think that's the only thing we know about this guy. But this guy, we can probably go this way here. So instead of like I've been doing this, instead of going this way now, we can probably do this in the reverse here. And then with 4, we can go back to 3. Because from 3 to 4, there's again an adiabatic relationship, reversible, isentropic. So we can use the same relationship as before. And for 4, I also have the pressure. Or is that going to be the same thing? It might be the same thing. Well, either way, we can do it. Because we have all those relationships, we have this guy too. So that means that we can have a relationship between V3 and V4. So it doesn't matter, you can do it either way. Okay, so let's go back in state 3. We know that V3 equals V2. We already figured this is 0.07. So that's done. We also know that P3 V3 to the K has to be equal to P4 V4 to the K. So we can use that to our advantage. And the other thing that we know is that there's a relationship between the V1 and V. So if I want to find P3, all we need to do is V4 over V3 to the K times P4. And actually, we do know P4, right, because it's the same pressure as P1. So that's a given from the start. So all I need to do is find this ratio here. And this ratio, I can combine the information that I know. I know that the Rx is V4 over V3, and that's divided by V2 over V1, which is 9.5. And we know this guy equals 2.25. This is all given on the statement. Okay, and we know that this fella here is 9.5. So that means that, well, therefore, V4 over V3 is 21.375. And then we can use this over here. So this becomes 21.375, 1.4. Okay, and then my pressure we already know is 1. Okay, so note that we could have found V4 first if we wanted to, or V3, doesn't matter, because we need either the P from this one to find this P here, or the V from this guy here to find V4. So either way, you could have done either way. So this rendered, what is it rendered? 7,071.997. So let's go ahead and approximate that. So it'll be 7,372. And that's kilopascals. Done. And now I have pressure and specific volume, right? So that means that my temperature is trivial once again. You just do P3, V3 specific volume divided by R. We have all that. 72, 0.087. And just mind you that if you're not approximating things like I am, you're going to get slightly different values, which is 100% fine. What did I get out of this? So my T3 is, so this is T3, 2,234.7. That's in Kelvin. Brilliant. So now we have state 3 completely defined, and we're only missing 1. So it's 3 down, 1 to go. For the last one, we already have a couple of things that are interesting. We know this ratio here. So we know that this fella here is 0.087. So that means that, so therefore, my V4 specific 4 will just be 21,375 times the 0.087. And so therefore my V4 equals about 1.86. Same unit as V3. And we're missing V temperature for state 4, right? Because we know the pressure, we know. You go ahead and write it down like so. State 4. Boom. This we can draw down here. And we know T pressure 1 equals pressure 4 because it's a constant pressure process. So this is 101.325 kilopascals. This is this, and we're only missing temperature. Again, temperature becomes trivial when we have these two guys. We just do pressure times specific volume divided by our constant, 0.287. Just for the sake of it, let's check units. We haven't done that in a while. Just make sure we're doing the right thing. Meters cubed per kilogram, and this is going to be kilojoules per kilograms per Kelvin. Kelvin, I don't have any Kelvin. I'm sorry, so Kelvin's going to stay. Kilograms, kilos and kilos, and then Pascal times meters cubed. That's the same thing as a joule. So we're left with Kelvin. Good. And what did I get? This is about 656.67. 656.7 is fine. Cool. So we need to find the whole thing. We can fill that table up now, the one that was asked from the start, because we have all pressures and specific volumes and temperatures for all the states. So where were we? Here we are. Okay. So this one is 20 Celsius, so this is straightforward, 293. This one we found to be 0.83. This one we found to be 2,368.8. This one we found to be 1.1. About 8 times less, about 10 times less. 7,372. 2,234.7. The same one as before, right? Because it's isovolumetric, isochoric transformation. This one has to be the same as the first one. The temperature for this one is 656.7. And this is 1.84. Last one, 86, right? 86. Cool. Okay, let's see if this makes sense. Okay, so let's relate this table to our original drawing. So we start at a pressure of 101 over here, state 1. Then when we go to state 2, our pressure should increase, and it does, right? It doubles, pretty much doubles. Actually, it's 20 times more. Never mind. Okay, so when we go up here, we're actually increasing our pressure. That makes sense. On state 3, we should increase our pressure even further, and that doesn't happen, right? So we go from 2,000 to 7,000. Cool. And then we should go back again to the original one. Okay, pressure checks out. Let's check now volume. So we start with a volume of 0.83. That's here, and then we should expect a decrease in volume. And that does indeed happen, and then our volume does not change on state 3, okay? Okay, and then we should expect the biggest volume of all on the last state when it expands, and that indeed happened. So to about 2 times our original volume. Brilliant. Temperature. We have the compression here from when we go from 1 to 2, so we expect our temperature to increase because our volume is decreasing. So pressure and temperature should increase. And then we have the heat addition process here. Okay, so once again, we should expect our temperature to increase. So we should go from 700 to 2,000. That makes sense. And then we're using our energy. We're using the energy to expand. So we should expect our temperature to decrease when we expand. And indeed, it does. Okay, cool. It does. So it goes from 2,000 to 600. Right, and then we have our heat goes out. I should have done the arrow this way, I guess, instead of this way. So heat goes out. So we should expect our temperature to drop from here to here. And we go from 600 back to 200. So that makes sense and checks out. So if we're off by a little.